Hello, it's Keith here, and this is lesson 13 of the so-called ChibiFighter assembly program tutorials, and this is the last one. We're covering the last system, the MSX2. So ChibiFighter is, of course, my little parody game. It's not really a full game, it's just a demo. I wouldn't really call it more than that. But basically, it's a little fighting game, and it uses a graphics engine that I refer to as Mintile. Now, this is a very simple tile map routine, and those tiles are then used to simulate sprites. So the characters you can see on the screen here are actually being built up of tiles, and so it's the same code doing both the job of drawing the background and drawing the sprites. And you can see they're a little bit flickery here because it's not using double buffering. But what we're going to look at today is the code that handles the graphics routines and also the interrupt based code that is used to play the music. The music you heard there is from my ChibiTrax music player, multi-platform, multi-CPU music player. And so that is what was doing that. We're going to look at the interrupt code for that. We're also going to look at the tile code. Okay, well, let's go over to our source and let's take a look. Okay, so let's begin. Now, there's going to be a separate tutorial series on the ChibiTrax music software. So all we're going to look at today is what it actually takes to get the music working on this system. Now, basically, we want to install an interrupt handler. The game is actually running from a ROM cartridge, and by default, the base area of the MSX memory map is actually ROM, and so we could page some RAM in there, but for simplicity, I'm not doing that because the MSX1, that isn't even an option. Usually, they don't have enough memory to do that. So what we're going to do is we're going to hook into the MSX's internal interrupt handling routine and add our own code to that, and we do that by changing the memory address FD9A, and we're going to put a jump. That is C3 as a jump command in bytecode, and then we're going to put the address of our interrupt handler, and that is basically putting in a jump to our interrupt handler at that address, and the internal firmware will run that for us during its interrupt routine. Now, the interrupt handler itself is here. ChibiTrax is my music software, and the play routine updates the music. This uses AF, BC, DE, HL, and IX only. It doesn't use IY or the shadow registers. Now, the rest of my code uses the shadow registers, but it doesn't use the shadow AF. So we're using AF shadow register and pushing the others and running the music update. At the end of this, we just do a simple return that passes control back to the interrupt handler of the operating system, and that is fine. Now, the only other thing we do need to do is we need to make sure we set up our registers of our VDP correctly, because if we don't have the VBlank interrupt enabled, we won't get any kind of music. So we're passing our VDP data here using this VDP init data list here. Here is the data here, and so basically these are the register numbers, and it's register 1 we are interested in, and it is basically bit 5. This bit here, if this bit is set to 1, then VBlank interrupts will occur. If we change that to a 0 and we run again, the game will run fine. However, we now have silence. The music is not working because the interrupt has been broken. So that's just something to bear in mind when you're trying to get interrupt working on the MSX. Okay, so there we go. So we have now got control of our interrupts. The remaining thing we're going to look at is the graphics. Now, the MSX2 has a rather odd way of working with its graphics. It's got a separate CPU with its separate VRAM. And so everything we need to do needs to be operations on that separate VRAM. We can tell it to transfer data around, but sending data from the CPU is going to be too slow. So what we need to do is we need to move all of our tiles to VRAM. And that's going to appear in an invisible area of the screen. And now we're using a single screen buffer, so 192 lines of the screen are the main screen, but lines 256 onwards are invisible. So what we're going to do is we're going to transfer all of our data that we need to play our game to that area. So we've got our font, we've got our title screen graphics here. These green ones are our background graphics for the levels. And then here is our character. So here's the player character. Here's the enemy character, and our players need to be able to flip horizontally. They don't flip vertically in this game, but they do flip horizontally. And so what we're doing is we're transferring each of the 128 player tiles. The first time we're transferring them normally, and then what we're doing is we're doing a horizontal flip of them, and we're transferring them a second time 128 lines down within VRAM. So if we wanted to flip this tile here, we would move 128 lines down to this tile here. That's the flipped version. So that's what we're going to do. Now, the graphics within my code are actually, we've seen you already, go away. The graphics in my code are actually 4 color, and we're going to convert them to 16 color via a tint. Now, the reason I'm using 4 color graphics on a 16 color system is I've had a problem in the past where the games will balloon in size. I write them on the CPC, 4 colors, port them to the 16 color MSX2, and all of a sudden I'm having to think about bank switching and things because the data's just got so much bigger. So rather than do that, I thought, Chibi-Akuma's, the game characters were always designed to be 4 colors, so I thought it was a good idea to simplify things and use 4 color graphics and use a tint to give the characters a bit of a different feel, and also do the backgrounds and things. So that's what we're doing here. So we've got a couple of things here. So basically we've got this send tiles function here, which will actually send the data to the VDP. Send tiles will do a single tile, so a background tile. Send tile duo will do the flipping routine. And then we've got various registers here. H and L are the source data for the graphics. That's the 4 color source data. IX is the X position. That's the horizontal position from 0 to 255. That should always be 0 in this case. We're always working with the Y position. IY is the Y line offset for the graphics data. We need to specify that again when we draw the tiles to the screen. And BC is the tile count in tiles. So 256 background tiles we've got there. I'm not sure if we actually have that many. We might have a few spare there, but the Chibi character, the player character, is 128 tiles, as is the enemy, 128 tiles, and the background is just 23 tiles, so very small. And we're using send tiles, and the D register is specifying our tint, our color tint. So we've defined our tints up here, and so basically these are masks to define the top 2 bits of our colors. So there's 2 pixels per byte, and so that is setting the top colors accordingly depending on our tint, and our palette is split into 4 color chunks. There's our palette here. So we've got 4 yellows, 4 Chibi colors, that's the main player character, 4 Eureka colors, that's the enemy character, and 4 greens for the background. There we go. So our send tiles routine basically is going to transfer the data from the source HL into the VDP via a HMMC command, which transfers from the Z8T slowly to VRAM. That's not used during the drawing of the graphics, far too slow, but it's used at this point. Now, if you need to know about those kind of commands, please see the other tutorial I did on how those work. I did a tutorial on every single command, so I'm not going to go over them here. I'm just going to discuss that they work. So we're transferring an 8x8 grid. We need to load in the first byte before we run the command, which is very annoying, but we have to do that. We're ORing in our tint there. So that is basically the first byte. We're then transferring that and initializing the sequence with this command here, and then we are going to jump and we're going to transfer the second byte. So we're loading the byte in again, shifting 2 bits to the right, and we're then selecting the second pair of pixels here, because as I say, we're converting from 4 colors down up to 16. So we've gone from 4 pixels per byte to 2 pixels per byte. So that's why we're doing that here. And we're then repeating, jumping back up to here and loading in the next pixel of the next byte until we've done all of those pixels, all of that pixel data. So that is loaded in a single tile. So we're converting our 4 colors to 16 via those 2 masks and that bit shift and those ORs. So that has done a single tile. What we then do is we move across the virtual screen by 8 pixels. If we've got to the end of a line, we then need to move down the line by 8 pixels. But once we've done this, we're basically we've transferred all of our tiles to VRAM. We just keep doing that until all of our tiles have been transferred, and then we return. So that's the basic version. That's the send tiles version for unflipped tiles. And we do the same thing when we are doing send tiles duo, but when we've done the first unflipped tiles, we then move down 128 tiles, which is 32 lines. I think I might have said 128 lines earlier, I apologize. 128 tiles, 32 lines, to the next position, and we're then going to transfer our tiles again, but this time we're going to flip the pixels. So basically what we're going to do is we are going to transfer the data in a sort of backwards orientation. So each of our lines is 2 bytes. Each of our 8 pixel source tiles is 2 bytes. So we're moving to the second of the bytes here, and we're then transferring the data, but this time we're flipping the first one by rotating it left. Last time we just loaded it in. This time we're flipping the first one and we're rotating it left. So that's flipping that. We're then shifting the second one even further, and that is basically flipping the pixels over, and we're then masking that with the D and sending the second one, and we're going to do that repeatedly for each line. Now after each byte, we're decreasing HL rather than increasing it, so we're moving backwards in the data, and then after each of our lines, we're then having to move to the end of the next line with these 4 inc HLs to be in the correct position to do that for the next line. So we're going down our 8 line tall pattern transferring each of the bytes with the pixels in the bytes swapped, and we're working backwards in the bytes of the line as well. So that is effectively flipping each of the tiles. So that's how we're actually getting our data into VRAM, and how we end up with this. This is a screenshot of the debugger, so that is literally what was in VRAM, if you can see the invisible 256 plus lines of video memory. So there we go. So that's how we are doing that. Now the remaining work is being done partially by Mintile, but that's going to be a separate tutorial series. That is the multi-platform code. So Mintile is doing the work of actually calculating the areas to draw, and it actually passes the draw commands to this platform specific code, and it's the do strip code that actually draws the graphics to the screen. So this will draw a strip, and Mintile builds these into either an entire screen or just a sort of small sprite area. So this do strip routine will actually draw a sprite to the screen. Now we're going to basically quickly transfer an 8x8 pixel block from the invisible area of the screen to the visible area according to our tile pattern. So we're going to have to use a HMMM command. As I say, if you don't know what they are, please see my other MSX tutorial where I covered all of the VDP commands on the MSX2. So what we're doing here is we are loading the X and Y position of our destination here into these memory areas here, and then what we're going to do is we're basically going to actually get the tile number that we want to show. Now BC is going to point to the tile map. If this is 0, then this is an empty area that we don't need to change. Basically we have a tile cache for the background, and we have sprites that do not use the tile cache, but in either case a 0 would be a tile that we don't want to draw. If we're doing the sprites, we don't want to do anything at this point, but if we're doing the background with the cache, we want to clear the cache to 0, and so that's what's going on here. And if we're doing the background, we are then zeroing the byte in that tile cache there. Now once we've done that, what we need to do is we need to take the tile number we want to show. We've got the 1 byte tile number here. We're then adding that to the value in DE here, which is the offset to the tile that we want to show. Now basically what we're going to do is we're going to divide the tile number by 32, and then that is the value that we need to multiply by 8 to get the strip number. There's 32 tiles on each 256 pixel wide line, and then those 8 pixel tall strips of tiles we can calculate by using those top bits here, and effectively multiplying that by 8 there. So now what we've got is our X position here from those bits there multiplied by 8, and our Y position from those bits here multiplied by 8. And so that is the source position within our tile data. So we've calculated, if we wanted to show that to ChibiCo there, we need to calculate that source position and then draw that to the destination position. And so now we've calculated that, that's what we're going to do. So what we're doing here is we're waiting for the VDP to finish its last job, and then what we're going to do here is we've got some RAM for Mintile HMMM. That is the command that we've built up to draw that's the sequence of commands to draw to the screen. We are then going to set up auto ink. We're going to set up the register we need to actually change, and then we've got the equivalent of 11 out I command here. This is the bytecode for a whole strip of out I's. This is the fastest way to transfer data. Now once we've sent that, the VDP will start doing that, and we can get ready to do the next tile. So we're changing our H position, moving across one tile for the next draw. We then are going to basically continue if we've not finished, and we're going to do the next one. Now once we've done an entire strip, what we need to do is we need to reset our firmware status register, because if interrupts occur, the VDP will read in from the status register, but if it's not the default one, the interrupt will not clear and it will cause us problems. So we need to make sure interrupts are disabled while we were doing this, and we set the interrupt default back with this command here. Now this my HMMM is a template. Basically this is the template. We load this template into memory, and this is all of the parameters that we need to use that HMMM command. This area is in ROM, so we can't change that, so the template is transferred to an area of RAM, and it's that RAM that's used to actually send the command to the VDP. Now that's the do strip command. The do strip reverse command is actually surprisingly similar. Basically all we do is we add 32 to the Y position, because all of the flipping code was actually done by our other our loading routine. All we need to do is change the destination from here 32 lines down, 128 tiles on for it to here, and so that is all we need to do to flip. We just change the loading address. So there we go. So a bit of a pain getting the data into memory and things, but the MSX2's graphics hardware it does actually give us a fairly decent job. It makes things relatively easy for us in the end. So there we go. That's all we're going to be covering today. Now, as I say, you can go to my source website, down the source code build scripts and all that, and you want to use it in any way you want. And we're going to go into the Mintile routine that does the underlying graphics routines for today. Now, I should point out the graphics were a bit flickery today. That's because I'm not using a double buffer. Part of the specification from the Mintile project, if you could call it that, is I only wanted to use a single buffer, and I wanted to see how good I could get things with only a single buffer, because for some systems double buffering is a luxury we can't afford, and for other systems, well, we might be able to afford it, but maybe we want to do something crazy. Maybe we want to use all of that extra memory for a really ridiculous number of tiles. So that's what Mintile does. It's a minimum tile function, very basic, so that is a limitation of it. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.